Okay, everyone. So you just finished up exam 2, and I think you'll agree it was kind of difficult. Let's talk about something that a lot of people had problems with, which was question 1. Okay, so question 1. We need to write a C++ function that takes as input a singly linked list pointed to by head and returns a pointer to a new singly linked list. So I've got to create a singly linked list. Okay, so the function declaration looks like this. So I've typed it over here so we can see it. And in this function, we need to create a new singly linked list that consists of nodes with the values of every other node in the input list. Also, the new list uses a special link called cross to point to the input node with the same value as seen in the illustration. So what does that mean? So let's take a look. Head is the very first node here, 1. And what I want to do is I want to create a node that mirrors that has a 1. And then I go to 2, but I skip it because this is every other node. So I go to 3, and then I create a node 3. And then I go to 4, and then I'm done. Now, whenever I created those nodes, I had to set the so-called cross pointer. That's the thing that connects this 1 down to this 1 and this 3 down to this 3. And you might be wondering, well, what is a cross pointer? Don't worry, we have the node struct right here, which you can also see in the problem. It's just a node pointer, like next, or if you're familiar with doubly linked lists, previous. Wonderful. So these little cross circles here are null, and we don't really need to mess with them too much. We won't need to do too much explicitly with that. Okay. So what we're going to do now is we're going to try and write this code, write this solution, and then we'll go over 3 different student solutions, and, the work that's there might surprise you. So, all right, we have got to start with what is, in my mind, the most simple edge case that we can possibly handle, right? Where if the head of the list is null, then we'll just return null, right? Because there's nothing to cross, nothing to set up. It's just one, done, and easy. And then we need this head 2 that it shows over here. So let's create one. We'll say head 2 is going to equal a new node from heads element, because I want it to have the same value. Now, one thing that you should always be careful about whenever you use arrow is the thing on the left of it null? Could head be null? Well, it couldn't, because if it was, we returned. So we're safe, so we're okay, let's keep going. So then we need is something to traverse through the elements of the first list down here, the one with head in it. We could actually use head itself, but that might be a bit confusing. So instead, we'll create a special node pointer for it, and we'll call it traverse, because that's exactly what it is that we want to do. And we'll start off at head next, because we already inserted whatever the value for head was. Let's also, tell you what, while we're up here, let head to cross be head, so that we can get that all set up. And then what we can do is we can say node pointer for current is going to start at head 2. So current will allow us to iterate through this list up here, this current list. Okay. So now what we'll want to do is we'll want to create a counter. So we can say int counter, and this will refer to how many nodes have been inserted. Well, we already inserted the head, so let's start the counter off at 1, because 1 node is currently there at head 2. We want to put more. And how many more? Well, in this case, we only need 1 more, but we want to write this in a more general way, right? This isn't meant to work just for the picture, it's meant to work for all sorts of stuff. So we need a loop. We'll say while traverse is not null pointer. Okay? And then it's actually really simple. All we have to do is we have to say if I is divisible by 2, that gives us the every other, sorry, not I, counter, divisible by 2. Then what we want to do is we want to create the new node. So what we'll do is we'll say that there's going to be a new node pointer called node, and I have to use the word new because I'm creating a brand new node out of thin air. Same way I created a brand new node for head 2, we got to create a new node down here, because obviously we're building up a new list of stuff, so we got to use new. Okay, so what we do is we set this to be traverse element, and let's double check, could traverse be null? Well, traverse is not null up here, so we're safe, right? Because it's not null, so we're good. Okay, and then what we want to do is we want to let node's cross pointer be the traverse node. This is the same kind of thing we did with head 2 and head 2 cross. Okay, so then what we want to do is we want to say current arrow next is going to be equal to this node that we created just now. And that ties the next pointer. And then what we want to do is we want to actually move current so that current will allow us to continuously insert new and new and new nodes. So we'll say current is equal to node, just like that. Phenomenal. So this has inserted a node for us whenever it was even. By the way, if we want to do every third node, we could just do modulus 3, or every fourth, we could do modulus 4. Apologies about the notification sound there. That's on my end. But what we'll do now is we'll try and move along the traverse. Because at this point, we're saying, well, traverse is not null, but I'm not changing traverse, which means that this is an infinite loop. So we have to change it. We'll say traverse is going to equal traverse arrow next. This is a really common way to traverse over a linked list. See the doubly linked list assignments if you're a little bit confused about how this works. And then what we want to do is we want to increase the count, because we have now seen one more node in the original list. So counter isn't how many nodes we've inserted per se, as much as it is how many nodes we've processed in the original list. So that's why process 1, process 2, process 3, insert, process 4, yada yada, right? Phenomenal. So what we can do now is we can return head2 at the end. And now the moment of truth. Does this code work? So I've created a makefile, and all this code will be on GitHub. So if I run make run, we can see here that our solution prints out perfectly. It's got the 1, the 3, and then it goes to null. And the list below is 1, 2, 3, 4, and then it goes to null, and all of its cross pointers are null. That just happened by default, but we set up our cross pointers correctly. That's good. So that then is the expected solution. This would be a perfect score on that question. But don't worry, almost nobody got a perfect score on that question. So let's go over some student-done code, some student solutions, and we'll discuss the different merits. Okay? So let's take a look at solution A. So solution A is not checking if head is null. So right away, we're running into an issue where head could be null. Another problem that student A is having is they have current and traverse set up. That's kind of nice, but they haven't set the head cross pointer. So we have two problems already, where head doesn't have its cross pointer set, and we haven't done a check for null of the original head. Okay, we have our counter, which they did call I. And while traverse next is not null, what we can do is we can say if it's divisible by 2, let current's element be traverse's element. Now the problem that we have here is this is replacing the element that is in head 2. We'd want to create a new node, right? That was something we talked about in the original solution, is we created a new node. We're not doing that here. So that's a bit of a problem. But we're then trying to set current's next pointer, a little bit like how we set the next pointer here, but again, it's quite different. What this is actually doing is this is actually iterating along this list while we're creating it, but that's not good, because this list is small compared to this list, and it's not yet fully built. So this means that current is going to become null really quickly. We increase the count, that's a good move, and we traverse. This is a good move, but there's an actual problem here, where if traverse next is not null, then we do this. But that means that traverse next can never become null, because if it was null, we wouldn't do this. And since we don't do this, this loop can never end, because this loop only ends whenever traverse next is null, which it can't exactly be. Technically, I suppose that it could, if it wasn't before we went into the if, and then we went and checked. But still, this if statement here is very unnecessary, as we saw from the provided solution. Now down here, they actually did go and try and set the head pointer, and they tried to do a check to make sure the head null pointer. Now you'll notice there are some issues, like they did equals equals here as opposed to a single equals. We don't really count off for things like that because we know what you were trying to do. Okay, so let's try and run this solution. It's called make run A in order to run that solution. So we had a warning because of the equals equals that I was talking about, but we actually had a segmentation fault, and that's because of this current that I was talking about. And you can check that. You can check your own solution as well. You just do make GDB, and then in this case we're looking at solution A, so it's make GDB A. We can put in run, and we can take a look, and it failed on line 16, exactly where we said it would, whenever current is equal to current next. Wonderful. So this is actually a very good solution. This earned a fair number of points. It's quite well done. The next student solution that we'll look at is solution B here. Now this solution is a lot more minimal, and sometimes that's okay, but this is unfortunately a bit more problematic. So we've created a whole separate node here called cross, and not ever set the cross pointer for anything. Remember, cross is a property of a node. It is not a node on its own. So by doing this and never actually setting the cross property, the student seems not to have understood exactly what the struct was. And that's fine. You are not alone if this code looks a lot like what you wrote or what you thought, because this solution is very, very, very common among the students. And I wouldn't worry too much about it. But there is a lot of problems here. So let's go through them. You're not checking for head being null. We've discussed that being an issue already. And we're not setting up cross pointers. We've discussed that's a bit of a problem. They are using head to traverse through. Remember, I mentioned we could do that in the original solution, but instead we decided to use this traverse node. This is actually okay. The big issue, though, is that they end up doing head next and then head next again without checking. So this would be the same thing as doing head next next somewhere, which means that they would also need to check to make sure head next next is not null pointer up here. So that's an issue. That already says that head could potentially segmentation fault, but that's actually not the worst of it. So whenever we created cross at the beginning, we created it and it has no next pointer. It's null afterwards. So whenever we say cross equals crosshair next, cross is now null. We've just done that on line 11, and then on line 12 we say null arrow element. Remember I said if you have null arrow anything, it's a segmentation fault? So sure enough, if we do make run B, because this is solution B, segmentation fault, and if we run it through GDB, where we tell it R for run, the program sure enough stops on that line 12 because cross has become null. So you see there's a lot of issues here, but they attempted to do next next before every insert, which would effectively do the every other behavior that we want. So it's not an awful solution. It just doesn't quite work. Using a counter, like what was done in solution A and in the provided solution, is a slightly better approach. All right, so we've now gone over solutions A and B. Now let's take a look at the third and final solution, which is solution C. So solution C is the shortest solution out of all of them. There's no loop here. It's just two if statements. And you might think immediately that this solution has to be wrong because there's no loop. And surely we need to loop to insert as many elements as we possibly could. If you don't have a loop, you might be in trouble. But the thing to note for this solution is that it is recursive. It calls itself. So let's step through it. We're not checking if head is null. So that is immediately a source of error where we could have a segmentation fault if head was null. So the student has already lost some points for that. This isn't a perfect score. But we create head 2 from head's element. And then we set head 2's cross to be the same as head. And if head next exists, then we can check if head next next exists. And if that's the case, we want to insert it by saying head 2 next is going to be head next next using this same procedure recursively. Now, you may not be able to visualize recursive code very well in your mind. This student clearly can, because this is an expertly written recursive function. So let's run it. Make run C. It actually works, which is phenomenal. So kudos to this student and to any like them that did a very recursive solution like this. It wasn't required, but clearly it was very simple. You just had to be able to wrap your mind around it and to think recursively. So this is a very, very well done solution, but let's go now to our main function here, which is what we've been running this whole time, and let's change the cases. So print list here is what we're using to generate this output. And the print list function is down here. You can look at it later if you want. The code is all online. But what we're doing is we're constructing the default list that we see there. and then we're calling the dual list function on it and printing it out to cout. Okay? What we wish to do now is we wish to, instead of doing it with this list that we've created, let's do it with null, test an empty list. Because as we saw, none of the student solutions were checking for null. And that is something that was very, very, very common. So you are not alone if you did that. So now we're printing out the list with null, and we're trying to do the dual list off of null, and we're printing the result of that, which should be null. So if we run the solution that we have developed, you can see that both lists are null, and there's no problem. Remember, the end of the list is designated with an X, and if there's no list at all, it's just an X. So now we can run sample solution A, which we already knew didn't work on the regular list, and they aren't checking for the special case. So sure enough, we get a segmentation fault. We can check solution B, segmentation fault, and even solution C, as interesting and well done as it was, segmentation fault, because none of them have done that simple base case check. And things like that during the exam are difficult to do. It's difficult to stay calm and keep that in mind. But in this particular problem, that's points. So it's a little unfortunate, but you're not alone. Even these really talented solutions were not quite able to, nail it and get a perfect score. But feel free, by all means, to try your own code here. You just have to replace solution.cpp, all of this, with your own code, and then you can type make run, and it'll run it. For those users that are on Mac, I suggest that you go into the make file and edit the compiler from G++ to whatever compiler you use on Mac. If you're on Windows, compiling with the Visual C++ compiler, you're on your own, and you'll have to figure out a way to make it work. But if you use Ubuntu through Windows Subsystem for Linux, or you run Linux directly, the make file is obviously sufficient. So let's now try and answer the two things that we put off at the beginning. What is the cost of building the linked list in big O asymptotic notation? Well, looking at the solution that we wrote, we're iterating over every single element in the original list, and there are n of them. And for each of the elements, we do a constant amount of work. We either just iterate, or we construct the new node, which is a constant size. So that, we will say, is going to be O of n work. Solution A does a very similar thing, obviously, to what it is that we're trying to do. This would also effectively be classed as O of n work, and the student would receive points for answering that. Solution B also attempts to do that. That would be O of n. Solution C, being recursive, even attempts to do that, and it is O of n. If, however, you wrote a solution that is O of 1, or O of log n, or O of n log n, and you are sure that your solution does actually run with that time, you should get the points for that. If you don't, feel free to go into office hours with the grader and discuss why they might have taken off points, because you would want to analyze your own function in Big O, and the correct function, and many of these student solutions were O of n, but there are some exceptions. Okay, and then the very last question, which is, which operations benefit with the above dual linked list? So the search operation is the one that most clearly benefits, because this system is a little bit like a mini version of a skip list, where the list is a little less dense, so we can go through it faster, and that allows us to check elements. Now, that would only actually be able to help us if we were guaranteed that the list was in order, because we would then be able to, like a skip list, search backwards and forwards. Because the list isn't necessarily in order, we couldn't say that the search is 100% better, but if the item is one of the every other items that has gone up here, we will find it about twice as quickly. So it's still big O of n, but it is a little bit faster. So hopefully that has cleared up a few things about this question. Again, all of this code is on github.com at the link in the description. You can download it as a zip file, or you can clone the repository for those of you that might be a little more Git knowledgeable. And I strongly encourage you to try things out and test your own solution. Obviously, you can fix your compile mistakes, because we try not to count off too much for that kind of thing. Awesome. then I hope that you all have learned a lot and that you will continue to pursue computer science.